Like the topic for today's paper reading is ALiBi, which is also called attention and linear biases. So basically, I'll just start with basically going through transformer architecture and what actually ALiBi improves on it. Like it doesn't actually improve transformer architecture, but it actually improves a part of it. That's quite critical, I would say. So as you can see, this is the transformer architecture, and we have something called positional encoding because like transformers, the way they work is different from RNNs. So RNNs, you have a time step concept where basically everything is treated as a series of tokens. Your sentence is treated as a series of tokens, and everything that comes next has value over everything that comes before. Like sort of like a recurrence relation. Transformers, on the other hand, actually have no concept of position. So you have to use something called a positional encoding to actually give those tokens a meaning. So like as you can see, there we have basically two decoder blocks. This is the whole transformer, obviously. So like we can use encoders and decoders like separately too, but this is the whole transformer architecture. So in the encoder block, we obviously have a multi-head attention, which I believe must be clear to most of you guys. So we have a multi-head attention, and then we have a feed-forward network. It's the same in the decoder, except we do a causal masking where actually we don't let the attention see what's ahead of it. So we mask anything that is ahead of the current like time step, basically. So that's why we use mask multi-head attention, because it employs a causal mask. So as I said, you might be wondering, why do we actually need positional embeddings? So like as I said, transformers model language as a set of tokens and not a sequence, which means man bites dog and dog bites man would mean exact same and give you the exact same representation if you don't have a positional embedding. So we were basically like there are a couple of types of commonly used positional embeddings. So like sinusoidal embeddings, I think they're the most common one. So in which you add a so you add a term which is like expressed in sign, and it is parameterized by the position of that token in the whole sentence. So that's the sinusoidal position embeddings. Rotary position embeddings actually were introduced in like GPT-J, like popularized in GPT-J, but used in Paraformer. So they basically, instead of actually adding those sinusoidal embeddings right into the at the end of the like layer itself. So here you can see like you have an input embedding, you add the position embedding as a plus operation. Rather, what they do is when you calculate attention, which will when how do you like I'll just go. So this is your attention. So when you calculate attention, rotary position embedding actually just add the sinusoidal terms. Basically, they multiply the sinusoidal terms in the product of Q and K. So that's how rotary works. T5 is slightly complex in a way, and it's very similar to ALiBi. So I'll probably take this later in addition to ALiBi and tell you what's actually different between those two things. So I'll just move ahead. So the simple thing is ALiBi. So ALiBi actually aims to remove the positional embeddings entirely, because the positional embeddings actually don't scale well beyond the maximum sequence length. So let's suppose we have a transformer model that was trained on a sequence length of, let's say, 512 tokens. So
I'm sorry, Abhimani, I have a question on the previous slide before jumping into
sure.
ALiBi. So what's the difference between these methods in terms of like the what do you call it, the advantages and disadvantages? Like what
advantages
how
and
good are they?
disadvantages.
Yeah.
Okay, so this is the advantage and disadvantages are more experimental results based. Hey, we did an experiment. Let's suppose we wanted transformer to write 5 paragraphs, but it breaks after let's say 2 paragraphs. In sinusoidal embeddings, rotary embeddings, it breaks after 3 paragraphs, and T5 may be going up to 5 paragraphs without actually losing context. So that's basically their only flaw. Like I'll just go through T5 in detail, like slight detail. Actually, because it's slightly complex, and once you understand ALiBi, it will be easier to understand. But if you want to give a quantitative estimate as to what is best out of these three, it is T5. and ALiBi is actually
Mm.
better than T5 too. So that's the whole conversation around ALiBi actually. So
Yeah.
quantitatively,
I'm
sinusoidal
assuming
embeddings
that.
are the worst. Yeah.
Yeah, I'm assuming that
So
the sinusoidal ones are probably the least computationally expensive, and T5 being the most computationally expensive out of
yeah,
the three.
T5 ones are the most like yeah. It's basically
Yeah.
I'll just show you too. So I'll just show you in the paper snippet too. I'll have okay. So as I said, like so, do you want to ask anything else before I actually move on?
I'm fine, but I think Sudhir did mention something. Is asking, have there been any papers studying the scalability of the transformers with respect to the positional embeddings?
Uh, I haven't actually come across a survey of positional embeddings in transformer architecture. If I find, I'll just like put it with the PPT I'll be putting if I find it, but not from my side. Like I haven't encountered any. So
Also,
the ALiBi paper actually compares these three this thing sinusoidal, rotary, and T5 bias along with itself. So that's I think close to what you might be expecting because it's pretty detailed in the appendix. So yeah,
yep, sounds good.
so yeah.
Thanks, Abhi.
So throughout the paper, ALiBi has been shown to work great with auto-regressive language modeling, which means like I'll just give you an example. Let me see if I'm sharing my. Am I sharing a window on a screen? I think I'm sharing a window. So actually, like I have, I'll just share back my actually screen because that's much better to use. Let me just do your entire screen. I'll just go here. Can you share my screen now? Like, hello.
Yep,
Hello.
yep. Yeah,
Yep.
yeah, yeah.
Okay, great. So I just wanted to break this term called auto-regressive language modeling. So auto-regressive language modeling is your GPT. It's basically your chat GPT said in a very simple terms. So you give it a word, they say, "Hey, it is sunny," so it will write today. Like something like Ivy is a framework that so it will write unifies all other frameworks, something like that. So if I have this chat GPT integrated in my application, I'll just type something random. Hello, the weather today is okay. I'm pretty bad at spelling things. Weather today is. Let's see what it writes. Okay, shit. Um, tell me something. That's the only hello. I'll just write something very simple. Hello world. Hello. So something like it's supposed to complete what I write. So that's basically what ChatGPT does. It basically completes your sentences based on a probability metrics. Like it tries to see what is more probable uh, uh, that can come after the word that you have written. So if I had written hello, and if it's a like a code writing model, it could have written word. So that's basically what auto-regressive language modeling means. Just predicting the next token. So yeah. So if you guys are familiar with how attention works, so I'll just go back to the attention slide, and if you can basically see this thing. So query and keys and values are basically extracted from the text sequence you have. Suppose like hello world. So you extract Q, K, and V in a way that in self attention, what you do is your query key and values are the same. It's basically the tokenized like representation of your text, which can be like something like this, 1 comma 2. So like 1 comma 2 based on your token ID. So basically you do your simple matmul, then you scale it. Then if you are using a decoder, you apply the causal mask, which hides the tokens ahead of it, and you softmax it and you return. You do a matmul with the values and return the attention weights basically. So here, what ALiBi does is actually it applies the this ALiBi bias, which is like it applies the ALiBi bias right before you do the softmax. So as you can see, query time query times key transpose is like how you calculate attention as usual. But when you are using ALiBi, you do this thing called m times uh, you call this like a penalty. So you apply this penalty where the tokens that are closer to the one you're observing get penalized, I think, less. Yeah. So the farther you go in a sentence, the less this term, actually, this term here penalizes your software attention weights. So as you can see right here, so this is the first position, and you can see this is 0 right now. It has no penalization. But as you go through longer sequences, you can see the tokens that are tokens that are more recent actually get penalized less. Like this token that is very far is penalized much more because it's a -4 term that has been added, and the ones that are closer actually get penalized lesser. So this actually this ALiBi has a recency bias where it favors a token that have been in the past like closer to the current token. So that's basically what ALiBi does. And M is a attention head, which is specific to the head. So we use this thing called multi-head attention, which is basically this same thing done over n times uh, across to calculate it for a head, which is like it is basically used to actually make your attention much more flexible with respect to seeing different characteristics of your text. Like it can observe very different behaviors. So that's why you use multi-head attention. And every head is assigned a specific slope.
Uh,
Yeah.
hey, Abhimanyu.
Anybody was asking?
Sorry,
Yeah.
not to be rude. I was just wondering if would this not like quite literally like for anything which has a long-term dependency not be quite so useful like for summarization or tasks like that because you're quite
It
literally
is supposed. Yeah, it's supposed to do that, but it doesn't. Like I'll just show you a result, which is actually the authors themselves were like, okay, shit, how does this even work? Because it is supposed to get better the longer you know, like predict text with it. So those are in the performance section. So even I thought it will get bad, worse because like something similar to what exploding gradient or vanishing gradient does in RNNs. Because if you keep on predicting, it is supposed to get worse, but it doesn't. So I think that could. I'm not sure because even the authors actually didn't give a proper reason why this happens, but they said on something on the lines because the recent tokens get penalized much more less. They actually help your context to be maintained over a longer sequence. So something on the lines of that. So is does it actually answer it?
yeah, a little bit. Do we have
Okay.
like some kind of results on
Yeah,
tasks?
yeah, yeah. We do. Yeah, we do actually. So I'll just I'll just go to the calculation of M first because it is essential to know how does this actually how does the whole thing fit into place like literally. So I just go to M. So this is very simple to calculate M because it's not a trainable parameter. You don't actually need to waste your expensive compute actually calculating something. So the starting term is 2 k power minus 8 by m, which n is the number of heads. So if you have n equal to 8, yeah, this is basically 1 by 2. And the common ratio is actually the same. This is like a mistake on my part, but the common ratio is exactly the same like this. So like, but if your heads are like something like 14 or like 18, you actually have to basically calculate it in a way like you get to the closest power of 2. So suppose in 14 you have the closest power of 2 is 8. You calculate the heads via this formula till 8. This is like, and then basically you add something like this, uh, 2 to the power minus 1 into 8 by n. So I think that's ahead. Okay, no. So actually, in this section, I'll actually go to the collab notebook, which is basically a light version of. Okay, where's my collab notebook? Okay, it's here. Okay, so I'll just actually just open it back. Mhm. So I just okay, laboratory.
I guess there's a question.
Yep. Yeah, yeah, yeah. You just
So
skip
like
because
how
I can actually. Hmm? Yeah.
so like how did they settle on the values of M? Like how did they make up this rule? I guess that's one question, and maybe a follow-up question would be,
That's actually in the paper. Actually, like they say, so it's basically what like sinusoidal embedding guys did. They tried a bunch of approaches and found out that this thing works best when you use a GP to actually express the slopes. So like this is the collab note which has basically taken from labml.ai's whole code. So like just to basically get the slopes quickly. So I'll just actually run this thing. I think I've already run this. So like get slope actually takes something called nheads is like, and it returns you an array which has like a total number of heads. Like I'll just, so yeah, I have run that function for I think 12 here. Yeah, they run it for 12. So you can see it like this gives you the values of head for the per head. So it starts like 0.5, then 0.25, and those goes all the way close to 0. So that's, and this is fixed, so you don't actually have to calculate it. So if I just actually just do remove this, get slopes of 8. If I do this, you can see it's like something like this thing, 0.5, 0.25. This is basically like reverse powers of 2. So 1 by 2 k power, I think 8 by n. You just do n equal to 1, n equal to 2, and that's how we calculate it. Like, so this is like they have like, so that's how you calculate m actually. So, and the remaining slopes, I think I can actually do this thing where I'll probably put a non to the power slope like 12. So that actually gives you values like this, like beyond what it can cover. So as you can see, these are the slopes that are calculated by via the original formula, but then you add a slopes that are calculated by the like additional term, which is actually greater. So you can see like this is like more than the earlier ones. So what actually these do is they let your attention attend to different things while as well as like changing their importance, because there's a different slope, so they can actually adjust how important or how flexible their whole attention term can be. So that's probably what it does. So does anybody have questions like, because in this it's like it's actually empirical. Like they have done a lot of experiments to come up with this thing. Even they say in their paper it is as finding something like this is as explainable as somebody figuring out how sinusoidal embeddings actually worked out back then in 2017. So that's probably the reason they use GP, geometric progression, to calculate this. So should I move
yeah, so
ahead?
I guess the greater the m, the more you're penalizing the further away tokens. Like, isn't this the
Yeah,
case?
so basically it's so actually if you think of it that way, when you do multi-head attention, you don't actually uh, manipulate anything the different attention heads give you. You just basically concatenate them all back to your attention dimension. But when you add an m term, which actually like straight up specifies how much important that head can be actually, because when you concatenate them, you basically concatenate different magnitudes of different attention heads. So that's actually post calculation they're adjusting the important, and that's fixed, and that has been shown to actually uh, like extrapolate over 4 times the sequence lengths on what they were trained on. That's basically like this is this basically works, I would say. I'll just go back to the performance comparison quickly. Like, okay, so yeah, so we have this thing called perplexity. Like, should I go through what's perplexity actually? Like, would that actually, uh, do you guys want me to go through that?
Yes, please.
Okay, sure. So I'll just go to the last slide. I have an appendix for that. Okay, interesting. So basically, like perplexity. So when you do your next step token prediction, which is like what comes after hello, is like a multi like class classification. So you have to actually find out what comes up after hello out of 50,000 words. So the way you do it in language modeling is you use a cross entropy loss. So like, which is basically, yeah, I'll just open a cross entropy loss and open a random Google image. That should do you good. Actually, like what's okay, this they have a good photo, I believe. Just yeah, actually they don't have math equations, so we'll just yeah, probably just to use this one. So you basically like okay, like kind of like penalize your next step. Basically, your next token should basically be like your next token should be the one that has the maximum probability of occurring given the past. Like that's like you are basically using conditional probability to actually see what comes after it. And the way you optimize it is called cross entropy. So your perplexity basically is like exponentiated cross entropy as it reads. Like just raise that the whole thing to e and you get a value that is supposed to actually tell you how general your model is actually. So that's basically perplexity explained. Like that's all of it. So before I'll just go back to this thing. So yeah, as I said, like ALiBi keeps the perplexity constant at higher sequence length. So which means the model stays general even if you predict more than it was trained on. So like these models actually were trained on 512 tokens on ALiBi, and when you try to infer them, the perplexity stays constant in case of ALiBi, shoots up in case of sinusoidal. Like this is how worse the sinusoidal actually is. Even rotary fails about like 2x the sequence length it was trained on, and T5 actually gradually decays with a like a lighter rate. But ALiBi basically keeps the prediction or basically the generation same, meaning it actually can generate very long sequence length, about like 32 times, as you can see in this graph, and still make sense. So these models are actually great for writing like hundreds of pages or like summarizing legal documents or something like that, and which requires a very high sequence length. So even I think GPT-4, the current one, actually has 32,000 sequence length. And if you train a ALiBi model on a sequence length of like 4,000, you can predict it up to 80,000, which I'll show you the model. There's a model that does that, and it's available on Hugging Face too. It's called NPT actually. So, and the same behavior in yeah, sure.
Quick question, Abhimanyu. So, like, the sinusoidal ones are only performed like at the beginning of the transformer. I'm assuming that ALiBi is like performed on every attention block, right?
ALiBi, yeah, they are basically performed on any attention block. So that's basically the difference in the implementation, because when you apply sinusoidal, you apply it to just the beginning. But in like ALiBi injects the position at every attention calculation step. So that's
Yep.
basically yeah. So that's basically, so the thing is that it keeps the perplexity constant at higher sequence lengths. It has no performance overheads like T5 bias. So I'll just, so as you can see, like the performance over like the way ALiBi works actually is by actually adding something that is constant to your attention calculation. Imagine this whole term right here being still there, but it is trainable now. So it actually adapts to what your input data is. That is basically T5. That is basically your T5 bias. So in a way, it works like that. So what it actually adds, it adds a lot of computational overhead that you have to train it with. So if you can see here, like the T5 bias is purple. It has the lowest training speed. It actually has the lowest inference speed on like a variety of sequence lengths. It basically goes down very sharply when you increase the input length, and it has almost the most amount of memory and like this thing. So it's, I think the rotary one is as much, because rotary one actually also multiplies those embeddings at every attention score calculation. But yeah, it's basically comparable. The memory requirements are very high, and as you can see, like 1.3, these were 1.3 billion parameter models, and ALiBi uses 11% less memory than sinusoidal, even in like the best cases. So that's why it is almost, if not better, in training a ALiBi model. So yeah, this is like the training speed for sinusoidal and ALiBi. It takes less memory, but it actually trains about as much while maintaining the perplexity. Like, so this graph actually also shows. So when you try to train your model on longer target sequence lengths, suppose like 1024, it takes more time. And if you basically increase it to 3072, it takes much more time. So it's comparable to the sinusoidal baseline. So ALiBi model actually have lower perplexity when trained on lesser tokens. So this graph is slightly harder to interpret, but I'll actually try to make it clear. Like ALiBi of a max target sequence length of 512 is demarcated by this triangle, reverse triangle kind of graph. So as you can see, on 512, it is better than the sinusoidal baseline, which is a purple square. And even when you actually infer the same model that was trained on 512 target, 512 sequence length, it actually is still better than the sinusoidal model that was trained on 3072 max sequence length, and it's still better. It's lower in perplexity, I mean to say. So, and if you basically go if you give it more sequence length, it actually gets you a much lower perplexity than any of the sinusoidal models can ever reach. So that is basically how effective ALiBi is when it's extrapolating to sequence lengths more than it was trained on. So, and it uses a very simple hack where you just modify the attention weights and add a per head bias, which is M basically. So it's actually relatively simple to implement. It takes, I think, a few lines of modification to an existing code. So, okay. This is the same observation, like, so like your training perplexity still stays like lower than your sinusoidal model. This is actually the same thing. You that the comparison between this thing and this thing, it's actually the same thing. So this thing. Okay, so this is a data set called Wikitext.
I just have a quick question.
Yeah.
How can we control the training speed? Isn't that like hardware related?
What? Training speed versus validation. So
Training
so
words
this
per
says,
second.
yeah, you can actually like, so if you have a, let's say if you have a training, if you have a trainer, you train models using a trainer, and you have a max sequence length, let's suppose 1000. And if your GPU, your current setup, which they haven't actually detailed in the paper, can do 5 passes of the data, and your batch size is, let's suppose 4. So you have 4 times 1000 tokens into 5 forward passes. So that is like 20,000 words per second you get per second that have been training. So that's how you calculate training words per second, I believe, because like I
So
haven't actually
basically, it
used
is
this
like
metric.
similar to batch size. Is this similar
You
to the
use
batch
batch.
size?
It depends both on your GPU flops and your GPU memory. So if you have a TPU which is like 64 GB worth of memory, you obviously have a much higher words per second. So, and if you, but whereas if you use something like a Tesla T4 which has 16 GB virtual memory, you would probably have 1/4 of those words per second, because you can fit smaller batches and smaller sequence lengths in that very GPU. So I think it's dependent on both your GPU VRAM, your target batch size, and your sequence length. So that's probably it. So yeah, so anything like, okay, I'll just go to the next slide. So like, yeah, so observation, this is the data set. These graphs are from Wikitext 103. So like as I basically said, the sequence line 512 model actually achieves a perplexity score of 18, which is still more than, which is actually like on the like this is a score on 3072 uh, inference length. Like if you infer on 3072 token, it still achieves this much score, which is, I think it's higher on 9 on when you do it on 512 only. Let me go back. So yeah, so this is the model. It is like above, it is around 19.8, and if you go to 3070, it's around 18.5. It is still better than sinusoidal baseline. And L equal to 512 model is around 2 times faster to train, and yet still outperforms the model, sinusoidal model that was trained on 3000 tokens. And all of these models can extrapolate and actually improve perplexity when handling more tokens. This is what actually I was telling you back then. So like this is the example I think Aparajit asked, where like how like does it actually, it should actually basically become worse like the sinusoidal or the rotary, or actually gets better. So like this is like the your perplexity actually goes down. So that actually makes the model more general, more uh, suited towards writing stuff. So yeah, yeah. So ALiBi models match the perplexity of sinusoidal model with twice the training sequence length. So you can see the validation perplexity almost being neck to neck to sinusoidal one, except I think here it actually ceases to be. It's still very close or within the margin of error. So, and this is when you use an ALiBi model with a max sequence length of 512 and sinusoidal one with 124. So you can actually cheat on you can actually cheat on training in a way that you can use a smaller model with ALiBi and still ensure a level of performance when actually predicting stuff. So this is the same graph I think for 100,048. Okay, yeah. Another thing is ALiBi has a strong uh, like a characteristic where actually it performs much better than sinusoidal's baseline on smaller data sets. So if you have a low resource language modeling task where it could be something like trying to write a language like Tamil or something like that, where the amount of corpus available is usually less, you can actually get a decent enough perplexity on even the lower maximum sequence lengths. So yeah, you can see like ALiBi has a perplexity of 9.79. It actually improves to 9.30 when you actually go longer, and it basically almost stays constant or like if not worse if you go to 4 times the sequence length. But sinusoidal just shoots up very high. Similar pattern for this thing. So that's basically, it's very powerful when actually trying to remember context. And since these results are on English, we don't actually have a comparative number for any other language, which might leave like a benefit of doubt if it's actually good for other languages. But they say that it is actually good for low resource language modeling, so I believe that might be the case. So I guess that was all actually. Uh, what do we have any questions? There's just okay. I'll just switch back to this thing. Yep. We don't tolerate duplicates here.
Am I audible?
Yeah. Hello. Yeah. Yeah. Like, so Maya, you speak what you want to ask. I can actually hear you. Can you just speak a bit louder?
Okay. I just have a problem with like even sinusoidal or ALiBi. If the positional embedding are not trainable, how do they extrapolate to new lenses? The part
it's
of
just
the model, the part of the model that corresponds to those lenses did not. It probably have random weights as they were initialized. right?
I don't- actually cannot make sense of what you're saying. Like, I think it's
Okay.
breaking it between, like, actually, can you write it in the chat box? I can read it from there. So, like,
Okay, I'll start right.
ad hominem attack on the authors of sinusoidal embeddings. Oh, nice. Thank God we are in terms. Good thing your question is this.
I think this
Yeah.
may be obvious, but I presume we don't use this for other tasks like summarization, for instance.
Actually, you can, but the thing is that the authors actually only tested it on decoded style models. So, like, they
Okay.
tested it on auto-regressive language model, and they found that the results are way better than what they expected. But they didn't actually write an ALiBi for encoder models. So, I'll actually have that thing also open. It's a encoder ALiBi, something like that. So there's an issue by the author itself where he says we didn't actually test it for encoder models, but yeah, this one actually. So, but you can actually make it work with encoder models, and they have actually outlined 3 approaches. Like, the main problem actually comes with is actually making the bias matrix. So I'll just actually, can I go back to that picture that was very nice? So this thing, the main problem comes with is actually making this ALiBi bias matrix. So, like, you can't with causal attention, you can always mask out the rest of the part, and that's what the ALiBi's basis of working is. It only works when it's only effective when it's utilized in the lower diagonal part, because that's how causal attention works, and that's their whole methodology of using ALiBi. But you can actually use it with encoder-based models, which are used. I think that's one way to summarize things. So, in a way, like, you can actually follow their issue and make it work, because actually I had actually implemented a BERT with an ALiBi attention, and it works. Like, I can actually get the validation loss to go down on a classification task using a BERT encoder, and it works. So I actually use this one only, the first approach, where I make a symmetric matrix. So I can show you the code if you want. Like, you can actually play around with it. So yeah, that answers it. For instance, question, if for any positional embeddings, if they are not trainable, how do they extrapolate to new lens? So like, there hasn't actually been a proper reason in the paper. Like, they didn't say ki actually we actually hypothesized this is supposed to happen with ALiBi. They just attributed it to something called recency bias. So if you can see that this very matrix, the terms that are closer to the current term actually are penalized much lesser. So ALiBi inherently favors the tokens that are closer to the current token. So in a way, if you think of it, if your last token is actually 1024 instead of 512, it will, when you auto regressively generate, it will always favor the last n tokens, which are less penalized, and it's supposed to somehow give it the context that it can go on without actually breaking. This technique might not properly work when you are working with very long text. Like, if you're writing like 2 pages of like 200 lines of code, then it might break, because you actually need to know what classes were defined at the line 1. So I think that's where it can fail actually, and nobody has tried it yet. So we don't actually have an answer for that too. So if that answers the question.